Okay, so a question came in on Scientist AI. It has to do with error surfaces, kind of a core concept in machine learning. It's something I introduced in the first lesson in kind of a bit of a narrow way, just for the sake of pedagogy, just for the sake of teaching it. It's all correct, obviously, what I said, but there is more nuance there. Of course, we would unpack a lot of that nuance in later lessons, but let's go ahead and unpack some of that now, because the student rightfully picked up on the fact that the way it was defined in the lesson, it seems like maybe there's still some confusion about how other aspects of machine learning might affect or help even define that error surface. Like, what does the data do? What does the model do? What does whatever. So we're going to unpack that a little bit in this whiteboard answer to that question. Okay, so let me just read the question so everyone knows what it is, what it's about. It says in lesson 1A, one of the last slides says error surface already exists independent of training, and you also say error surface you train on. What do you mean by that? Question goes on and says, my guess is that the error surface is set by human bias. Who decides what features are relevant to use for each row and the weights to be assigned to each feature? If I'm on right track, it only explains initial conditions. Example, position on a golf course. But does not predefine the golf course. In other words, who makes the golf course since no two are the same? So it's kind of like, end of question. I think what he's getting at is almost, he's in need of a bit of a geometric interpretation maybe of what that error surface is and what goes into really defining it. And is there anything beyond kind of the statically defined loss function that we looked at in the first lesson? Okay, so yes, in lesson 1, I said the error surface already exists independent of training and is defined statically by the loss function, which of course is 100% true. But let's dig into some of the more nuanced aspects of it so you can really get a sense of what that is. Now, this is how we define the error surface. Well, this is the parameter space, and the error surface exists within it. Okay, and this is just, this has got some kind of quote-unquote topography to it, and you usually have kind of the visual of a ball trying to roll downhill, find some low point, like a local minimum, and that would be equivalent to essentially finding a really good set of parameters so that in machine learning, when you try to find the function that maps input to output really well, it's doing a good job of that, right? What are the parameter values that allow this mapping to happen really well? It's the low point on the error surface. And I defined that, I basically said this surface here that the ball, quote unquote, is rolling on as you try to find parameters during training is essentially statically defined by that loss function that we looked at, which is true. But there is more to it than that, okay? So let's separate 3 different things that often get conflated. 1, what makes the golf course, to use the same analogy as the question. 2, what is the error surface precisely? And 3, where does human bias actually enter? Okay, so who makes the golf course? The golf course being the analogy being used for what, this actual error surface. Okay, so no single person does. The quote-unquote golf course, or the error surface, is jointly determined by 3 things. Okay? 3 things really go into that. First is what we would call the model class. And this is literally just the model that you're choosing. So it could be a linear model, it could be a neural network, whatever it is. 2 is the loss function, which we already looked at. And we'll take a look at that a little bit again. And 3 is the data set itself, what data you're using. So technically, all these have a role to play in carving out or jointly defining that error surface. Okay? Monoclass, which should in some sense already make sense, because when you choose a model, you are choosing, imagine like the analytic function that you're looking at of the model itself, it defines parameters a certain way, or the way the parameters get used, so it's already defining the parameter space. Loss function is how wrong something is, so that's obviously playing a role. The data set, we're going to see how that comes into actually helping carve out how, the space of possibilities that the errors can play out. And so we'll get into that. But for now, just understand that these three things technically go in to defining that error surface. Once those are fixed, the error surface is fully determined. There's no freedom left, meaning training does not sculpt it. Training only traverses it. And that was the main point I was making in the first lesson. So training is not coming in and changing the error surface. It's just playing on that. It's like a golf player showing up to the course and just playing the game at that point. The whole golf course has been laid out. Okay, so who makes the golf course? Model class, loss function, and data set make the golf course. So let's dig into the model class itself, just to make sure we understand that. So the model class determines the parameter space, right? Which parameters exist and how many there are, and how changes in them affect the model's behavior, right? So since the error surface lives in parameter space, the parameter space is partially defined by the model class. It's really that simple, right? And you know, so just think, like, if you have, remember we had the linear model here, and we had parameters from the weight vector and the bias. So it's right in there. We know that this is defining essentially how parameters get used in the model. That's carving out the literal parameter space that the error surface lives in. So by choosing this model, we're choosing kind of part of the almost the ground, if you will, that the error surface is going to live on. And that ground has an effect. So that'd be a linear model. So that'd be weight vectors and biases. It could be a convolutional neural network, right? Filters, strides, and shared weights would kind of define what that parameter space looks like. If it was a transformer model, it'd be things like attention matrices, projections, embeddings, right? So different model classes literally have different coordinates in parameter space, because that's really what a model is doing, is it's defining the space of possible parameters that you can tweak in order to get the mapping between input and output to go that much more effectively. Okay? So hopefully that makes sense. I think that's pretty straightforward. So let's do a geometric interpretation of that to kind of stick with the golf course, right? Think of the model class as the allowed directions and deformation of motion. It's the ground, like I said, on which the surface can exist. So from a geometric role standpoint, the model class defines the parameter space itself, which means its dimensionality, its coordinate system, how a small parameter move might deform a prediction, okay? Think of it like, I think this is a real geometric way to think about it. It determines whether moving diagonally does something different than moving straight, for example. It's almost like getting into the kinematics of what would play out on the error surface, right? Like, is this different than this? Is going straight different than diagonal, right? Another way to think about it is two steps of equal length in parameter space can produce widely different prediction changes depending on the model you choose, okay? So it carves out the parameter space, and it kind of dictates how things, quote unquote, are able to move within it, or what they mean when they do move. If you want to think about what the it is that's moving, it's kind of like maybe the ball, obviously, it has to roll down that surface when it comes to training, right? So the training is not changing it, but the space is carved out by the model class. Okay, another one is the loss function. And we dealt with that. And that was the main way that I defined essentially where that error surface was coming from in the first lesson, right? So whereas the model class determines what motions in parameter space do, the loss function determines how those motions are valued. And that should sound familiar from what we already learned, right? So that is, you know, what it means to be wrong, how deviations are penalized, which errors matter more than others. Okay, so the loss does not change the model's behavior, it only scores it. Okay, so think of, let's get into some geometric interpretation again. Think of loss function, and we did this a little bit already, as the vertical height and steepness, right? How the wrongness is measured. Okay, so the loss function assigns a scalar height to each parameter location, right? So again, you're in parameter space, and you got your error surface. Think of it as there's a little bit of heights here, right? It's almost getting into kind of a quote-unquote topography, if you will, of the error surface. It's a different piece of information. So you could have the same parameters, same predictions, but if you have a different loss, then you would have different heights there, because the way the wrongness is being measured is different. So this is essentially literally where the surface comes from, which is why I focused on the loss function as being, you know, that definition of the error surface itself, even though model class and data set come into it. The loss does not change where you can move. It changes how painful each location is another way to think about it. Okay? I'll bring all these together in a second, but let's focus on the data set now. You can think of the data set as kind of being where the terrain is shaped. So where hills, valleys, and basins appear, right? Because again, we're thinking about this very geometrically. Where are the low points? Where are the high points, right? So from a geometric role standpoint, the data determines where in parameter space, let's say, the surface is bending. Okay, so each data point contributes a constraint. Aggregated data might carve out things like valleys, right? Conflicting data might create saddles and flat regions. So you can think of it as each data kind of pulling the surface up or down somewhere. Data controls where the surface features appear, essentially. So if you take those, you might kind of think, okay, I kind of get it. But, let's say the data set and a loss function, in a way, kind of both sound like they're doing the same thing. Like they're both kind of, quote unquote, the topography of the surface. And even though I know that one measures how wrong something is, the issue here is we're trying to come up with geometric interpretations of what these three individual things are doing, right? Again, that model class, which defines the parameter space, right? The loss function, which really is that surface, but then also the data set itself kind of anchors things within it and kind of dictates how things are going to behave. It's hard to think of these three things independently because they're not independent, okay? These things are really synthesized together, and only in concert, only in working together does the error surface actually become instantiated, become a real thing, okay? So really, there is no error surface without all three. And in fact, thinking of them separately is confusing because they do not actually exist independently, right? One needs the data to collide with the error definition in the loss function, and that collision must be dictated by the kinematics of the model class. Only then does the surface actually arise. So that's why, geometric interpretation kind of works up to a point, but you got to remember, even this three-dimensional picture is not real in the sense that this would be very high-dimensional. Could be 1,000, could be 1,000,000, right? Deep learning networks can get into billions of parameters, right? So what does the data mean? What does the model class mean? When it comes to the model class and the deep learning network, we can't even look at what the function looks like, right? Because you can't have an analytical expression of it. It's much too complex. Of course, these loss functions can get fairly convoluted, but usually aren't too bad. And of course, the data set can be massive and extremely high-dimensional. So conceptually, it's just important to understand that these three things together come together to produce and instantiate the error surface. And they do have different roles, but the different roles they play, we can use analogies, but they really have to exist as one altogether, okay? But at a high level, you can say, look, they carve out the parameter space, right? They give a definition of kind of the heights in that space, the quote-unquote kinematics in that space, what it means to move in different directions. Like so many mathematical approaches that do anything like this, it's just trying to really define the geometry, right, within a space that is high-dimensional. You see that in a lot of areas, and of course, it's that in AI. Okay, so model class determines how predictions respond to parameters, the loss determines how prediction differences translate into error, and data determines where those predictions are evaluated. The surface exists only after all those three are combined. So that is the answer to what is the golf course. Okay, so I hope that made sense. Now, there was so that was the first part. And then the second part of that question was, what is the error surface precisely? Okay, so we did it conceptually, we kind of did it geometrically. That might not be totally satisfying, so let's go back to some of the mathematics. Let's take a look at defining the loss function. Now, originally, the loss function that I showed looked like this, right? We had our loss, we had a parameter, and remember we were aggregating across the entire data set, right? And we said, okay, so this is going to be, all the rows of the data set. And of course, when we were doing it, we had, right, essentially this linear model in here. And then we had to take the difference between whatever the output of that linear model was, that was y hat, and we just called this y over here. And this was the true label, right? And then this was, of course, a Euclidean square distance between them based on the norm we were doing. So we did this all in lesson 1, right? So this is the loss function here. But you could say, well, actually, this is the error surface. And you could, so then it's like, well, is that the same thing? And this is kind of where some of that confusion comes. Well, let me write this, I'll just do it down here, a slightly different way. Looks almost the same. I'll do it as L theta. Okay, and we got the same aggregation that we were doing. Okay, and then I'm just going to actually put loss in here. Okay, and then I'm just going to say, we had some function parameterized. We got the data that it acts on. and then we compare it to some true label. We can just do this row by row still, and then it looks like that. So it almost looks the same, but notice that I'm putting the loss in there. So this looks a little bit confusing, right? Like, what am I doing? Putting a loss inside of a loss? What is that? Well, this is actually the error surface. And so that doesn't mean this is wrong. These are just basically two levels of abstraction you're looking at. If you look at here, we got the square, right? Here, this is actually what's defining, right, the loss function, right? Is the way you're taking the difference between the true label and the output of the model, right? It's measuring the wrongness, right? So you could just say there's some loss here, and then the function comes in with the data and has the label, and it gets aggregated, and that whole thing defines the error surface, right? In other words, going back to what we said before, remember I said model class, data, and loss function lead to error surface? Okay, so the model class is the function right there, right? We were using the linear model before, but that's the function right there. Sorry. And so we could say the geometric role of that is how lateral motion affects predictions. The data, okay, is basically right here. He is right there, right? And you could also say, I mean, the label is in the data as well, so you can actually say this is part of it, right? The y-on. So where constraints are applied, you could call that. And then the loss function is whatever it is you choose acting on, right, the function of the data right there. And that's, of course, how the discrepancies are scored. So the full thing is actually the error surface. So I think that is why it might have led to a little bit of confusion in lesson one, where we're looking at a very specific case, right, of the loss function. But really, it's the whole error surface, because this part is measuring the difference, but then other things go in, you're aggregating across the whole data. So this would almost be a more accurate kind of way to say maybe what the error surface is. But it's the same idea, right? But now you understand that it's the model class and the data that's used and the loss function that gets defined that really goes into fully specifying what an error surface is, okay? Okay, there's one more point, which is where does human bias actually enter? Okay, so the person who asked the question, they were saying, well, the error surface, well, they were guessing. They said maybe the error surface is set by human bias. That is partly true, but we need to be very precise about why and how that is. So humans can influence the surface indirectly by choosing things like the features, feature selection. Okay, now that can actually influence the coordinate system of parameter space. Now, at first, that might sound a little weird, because if you remember, when we were looking at features in the data set, we didn't really directly relate that to the parameter space, right? We said, like, you've got a table of data, you choose features, that goes into the feature space, not the parameter space, the feature space. So if that's ABC, so this is A, feature B, feature C. The data lives in that feature space, right? The parameter space was something different, right? This is where the parameters are playing out. But if you take a look at the model, okay, to use that linear model as an example, we can see that the parameters live in what you might call a dual space of features. In other words, choosing features literally chooses which parameters exist. Or another way to put it is the dimensionality between the weight vector and the data had to be the same, right? So in other words, if you're choosing the data, right, and that data has a dimensionality to it, D, which is like the number of columns in the table, you're also technically choosing the dimensionality of the weight vector as well because of the way that dot product is formed. So when you do feature selection, you're not just working with coordinates of the feature space, you're also, in some indirect way, dictating the coordinate system of parameter space as well. Okay? And then, so that's feature selection, another way that human bias can kind of, so it's biased because humans are choosing which features to look at. Right? This is less the case with deep learning. Deep learning obviously still has bias, you still have to choose the data, but it's kind of grab as much as you can get compared to being really specific about what features you're going to grab in more traditional classical machine learning or statistics, either because you don't have access to the data or again, you're almost trying to design it a little bit upfront, right? But in all cases of machine learning, that's where the bias can come in, and it does affect the parameter space, right? So going back to the question, there is human bias that goes into the definition of the error surface itself. Model class, right? The dimensionality and geometry of the surface that we know is affected by model class. So if you're choosing a model, am I going to do a linear model? Am I going to do deep learning, something Bayesian, right? The loss function, the notion of wrongness, right? When you define the loss function, right, maybe we're doing the squared Euclidean, but that's not the only option, right? There's different distances and different things you can use to define what wrong actually means, right? So you can see it conceptually, a lot of that is just like things that we do as humans, right? You know, your value system might be a little bit different than mine, so maybe our notion of morality or wrongness is not exactly the same, right? The model that we use is kind of the lens with which we think inputs map to outputs in the world, right? It's very analogous to just how decision making and learning happen in general, right? But critically, it's important to note that humans do not choose the weights. They do not choose the gradients. Remember from lesson 1 when we're looking at these parts, and they don't really choose where the minima are in any direct sense. You should think of those as emerging mathematically from the choices of what we talked about between model class, loss function, and the data set. So let's fix your golf course analogy just a bit to make it align with everything that we just talked about. Okay, so the person asking the question said, initial position is set, but who builds the golf course? So here's the correct mapping, I would say. If we have to use this type of analogy, you can say, well, the course rules, like the physics of the grass and the slopes, would be like the model and the loss. The terrain shape would maybe be the data set. The ball starting position would be the initialization. And a player walking downhill would be like gradient descent. It's about as close as we can get. But again, you got to be careful, right? Because it's not like these are orthogonal things to look at. Model class, loss function, data set come together as a single synthesis to uniquely carve out and define that error surface. It's really not correct to think about the different pieces playing totally different roles. They come together. Okay. So yes, I used a somewhat narrow definition of the error surface in lesson 1, where I only showed the loss function, basically said that statically defines the error surface. It was to help introduce the fact that the error surface exists independent of training and is static during training. Both those things are 100% true, right? The main point I wanted to drive home is that training does not sculpt the surface. But good on you, the person asking this question, for noticing that there is more. There's a more nuanced talk about what all actually goes into defining an error surface. The fuller definition, which we'll get into in a lot of the later lessons, you could say, if you want to sum this up, is just basically being aware of the fact that the error surface is defined by the composition. Let's just say error surface. Okay. Is, if you probably don't know too much about maybe the notation for compositions, but if we're composing, right, the loss, the model class, or the function you're choosing in the data set. Right? That's kind of like the simplest way you could kind of say what goes into it. Okay, you're composing that. Okay. Anyways, so most of my answers to questions will not be this long, but I thought this would be a good one to actually whiteboard out, almost treat it as its own mini lesson, and hopefully that all made sense. Of course, if you have any other questions, just let me know. Thanks.